Hello everyone. In this video, we will learn how to find the second derivative of parametric equations. Well, remember that when we have parametric equations, basically we have one equation for x and y, another one for y, both gives x and y in terms of t. Then you can find the derivative of y with respect to x. This was a theorem which says that it's enough to find the derivative of y with respect to t and then divided by the derivative of x with respect to t. Okay? Here the key point is that this is a function of t. In other words, dy dx, maybe the third variable, is also a function of t now. Okay? Here, then you can go ahead and say, what is the second derivative? How do you find this one? Well, the one first thing that you may try to do is that, okay, dy, then I differentiate twice this guy with respect to t, divided by twice with respect to tx, and divide these guys. Oops, I'm using the wrong notation here. This must be this. This is not true. And the important thing to note here is that the second derivative is basically the first derivative of the first derivative. Yeah? Now, if I call this one as z, I have x in terms of t, and I have z in terms of t. We are trying to find derivative of z with respect to x. Then what we do, we apply the same theorem, and this time this will get d dt of z. Well, in this case, it means that dy dx. So you find the derivative of the first derivative with respect to t, and then divided by the derivative of x with respect to t. So there will be some work done here, but basically you turn it back to another parametric equation in which you have x equal to f at t and dy dz as the second variable in terms of t. So this is a new parametric equation and we are differentiating that guy with the rule that we know already. Let's see this in some examples. So find the second derivative of this guy. So here, first we have to find the first derivative, and the theorem says that you differentiate with respect to t, both of these ones, and then divide the derivative of t y to the derivative of by the derivative of x. So here this means 2t plus 2, and that means 3t squared minus 6. Now, this is the first derivative. If we are looking for the second derivative of y with respect to x, this would mean that you find the derivative of the first derivative with respect to x. So in other words, if I want to write it in different ways, so x is defined in terms of the parameter t. The derivative is defined in terms of t. Now we want to find the derivative of this guy with respect to that. This is exactly what we do when we're trying to find the first derivative. So we find the derivative of the first derivative with respect to t, and divided by the derivative of x with respect to t. Okay, so then that means that, okay, this is just quotient rule. I have to differentiate this one. That is 2 times 3t squared minus 6 minus 6t times 2t plus 2 divided by 3t squared minus 6 squared. And divided by dx dt, which is the derivative of this guy with respect to t, which gives us 3t squared minus 6. And if you do set this one, that the result is going to be, by the way, these guys are going to cancel each other, this one and that one, and the remaining is going to be minus 12t, that's coming from this one, and minus 12 in the numerator. In the denominator, we had this 3t squared minus 6 squared. We have to multiply it to the same thing, so this will be power 3. Okay, for the second derivative, you have to do a little bit longer way. And another formula, another thing. So remember that the second derivative tells us what is concavity. If the second derivative is a positive, that means that the curve is concave upward. And if the second derivative is negative, that means that it's concave downward. So, long story short, means that we have to find the second derivative of these parametric equations, starting from the first derivative. This is going to be minus, dy dt divided by dx dt. This is e to the power 2t plus 2 times t e to the power 2t. That's product. And this one down there is e to the power negative t. Okay, so that I can factor out e to the power 2t. There's a minus sign. I will bring it. Okay. Note that here now I can take this to the numerator and write it as, by the way, this minus also can go up, 1 plus 2t e to the power 3t. This is the first derivative. Now we are looking for the second derivative. It means that we have to find the derivative of the first derivative. This is, then you differentiate first derivative with respect to t and divide it by the derivative of x with respect to t. Let me write it in different color. So derivative this guy with respect to t, it will be minus 2 e to the power 3t minus 1 plus 2t multiplied by 3 e to the power 3t divided by negative e to the power negative t, the derivative of x there. You can factor e to the power 3t there, and the remaining there will be negative 2 minus 3 minus 6t. And do the same kind of work that we did before. So we go ahead and simplify everything here. So this will be 6t plus 5. And again, so I multiplied that negative sign inside. I also can bring this in up, so this will be e to the power 4t. We want to see where this is positive, where it is a negative. So I set that one equal to 0 and see that, okay, e to the 4t, it must either e to the power 4t must be 0 or the 6t plus 5 must be 0. But this is always non-zero, and that means that for sure this guy needs to be 0. So that means that t must be negative 5 over 6. So we found where the second derivative is 0. This is negative 5 over 6. And now we have to fix where if it is positive for values bigger than that or negative. So just plug in one value, something like 0. If you plug in 0 here, this is 5 times e to the power 0, which is positive. This is negative. So this function is going to be concave. The graph is going to be concave upward for values of t bigger than negative 5 over 6, and downward for values of t less than negative 5 over 6. If you know the graph of the function, you can go ahead and do a little bit of more work and exactly find which parts that will give us negative and positive. Actually, you can plug in and this value in the equations, and it will tell you from what Cartesian point on it is going to be concave up and on which part it's going to be concave down. Okay, so that's what we were looking for, and we were able now to find the second derivative for parametric equations.